So it's a great pleasure to have today with us Jens Paaske, a very good friend and colleague. Jens is a professor at the Niels Bohr Institute, Center for Quantum Devices in Copenhagen. He did the PhD some years ago. not many years ago in Copenhagen.
Decades ago.
Let me say, we are recording already. And he did a postdoc in Karlsruhe in Germany with Peter Wolfli. You know, he's an expert on strongly correlated systems, mesoscopics, superconductivity, many things. And condo, yeah, it's true. And during the last few years or so, he's been working on this kind of hybrid SNS junctions, Shiba states, and the physics, these kind of problems. And today he will be telling us about how this microwave response of Yu-Shiba-Rusinov states, what can we learn from this? And welcome, and we are happy to have you here.
Yeah. Thank you very much. Thank you very much. It's a great pleasure to be out again and to finally make it to Madrid, where I have never been before. And I see now that it's a great mistake, but there's still time to come back, I hope. So what I'll tell you about today is really sort of my personal preferred fruit fly of hybrid systems. It doesn't get much simpler than this without becoming entirely trivial. Still, this Yu-Shiba-Rusinov state here has been with us in Copenhagen and other places for some years now, and Gorm can testify to that. He has also been a good friend of this phenomenon. And today I'll just add microwaves to it, and that's really been an educational tour for me and for Cecilia, my PhD student, and we worked together with Alfredo on this. And it was just to now that every lab is full of microwaves and that DC is sort of an old story, then and that every qubit on the planet seems to require nice microwave electronics, maybe it's time to do a new version of what we used to do. So that's what this was, an entry into this. And the first picture here is really something I borrowed from this paper down here. It's reflectometry from anatomic contact, and there are some black spots and some gray spots and some white spots. And we'll return to these a few times in this talk. And basically, now I just grab figures from this paper here, from which I learned a lot. You should just imagine an LC resonator here with a mutual inductance to a circuit here, which is superconducting. And then there's a region here that is sort of my matter system. This is the light and this is the matter, if you like. And then you have a few options of driving this system, if you like, but I won't do that today. Well, in the first part of the talk I won't, but if I get to the last part of the talk, I will skip the readout and then I'll only do the driving instead. So let's see how far we get. And really, this is not that hard. It's a harmonic oscillator, so phi and q are my conjugate variables. Oops, let's see. I'm losing my coordinates here. I don't know if it should be.
Just use the laser.
Okay, good. Yeah, so harmonic oscillator, that's fine. I've written that up here. We all know that one. And then I just do linear response to the circuit here. And the circuit is now this response function here. So we'll get to that. And here's the coupling in proper units. And all that I need to learn from this is that there's a shift of the frequency of this resonator, and there's maybe also a damping. And I just want to calculate that for my favorite system in here. And as I said, well, before I say that, so this system will be a superconducting junction, and most often that has a personality captured by formulas like this. Here there's some subgap states that depend on the phase difference and whatnot. We'll get to that. And that's basically what you explore with this spectroscopy here. So again, I just grab a few pictures from this paper here where they explain how to investigate such junctions of short length or finite length in spin orbit. There's many options, and this has been a field for quite some years now, with a lot of expertise that, as I said, I'm just learning now. So this here is a nice example. It's very recent. It's an indium arsenide wire covered with aluminium. So it has this epitaxially grown aluminium covered out here, and then it is etched away in here in a 550 nanometer region. So it's like S and S. And there's some Andreev bound states in here, reflecting back and forth from between the superconducting mirrors. And underneath there's a gate, which you can do things with to tune this system. And without going through the whole paper, here are some beautiful measurements, phase differences, and again this spectroscopy, these frequency shifts here. Now this is a special version of it, but all I want you to take away from this is that this is a field, that local people here. This is Francisco's theory work here together with Alfredo, and it is the Saclay group doing the experiments and some Copenhagen people providing the wires. And so here's a model. And what I want you to notice today is that Francisco seemed to be needing some interactions for fitting this particular set of data. It is something about a feature here that needs to be matched to experiment. And for that, interactions seem to be needed. They are not always needed, but in this particular case, it was not really possible to fit the data, unless you do that, and then it was possible. And this is very well understood what happens here, I believe. Let me show you one other example. It's again, and it's an indium arsenide wire again with two facets of this hexagonal wire covered by superconducting aluminium. It's 350 nanometer normal segment here. And again, here's a resonator coupled to this, and here's a transmission line where you read off the resonant frequency of this, and you can read off the frequency shift and so on. And you can also drive it. And I just want again to show you here's an S region, which is described in a slightly simpler way because the data have less features, right? So here there's not quite as many lines to think about. And in this paper here, they have a fairly simple model where they managed to describe this. And I throw up here the fitting parameters, and then I'll get back to a possible alternative for describing this in slightly better numbers. But this is really details. But you see, this is not exquisite resolution or anything. This is just sticking in this device and seeing how does the frequency shift of the oscillator. So we'll get back to this. And that's in this paper here, done at Yale by Vala Fatemi, who's now at Cornell. And again, it's the Copenhagen wires. They were made slightly different. I believe the Saclay ones were full shell. This one is just two facets. But I'm not entirely sure what makes the difference here. The length of the region, the normal region here is a little shorter, but that's it. Okay. So on the menu, I just have my fruit fly here, the Yu-Shiba-Rusinov states, which coming from Kondo physics and so on, this was a natural extension once everything became superconducting. So that's why I've been working on this for many years now. And usually this is something that you know best from STM experiments, but we have been exploring it in many years now with quantum dots instead, so artificial magnetic moments, you might say. And I just want to do 3 different levels of, actually 4 different levels approximation. So I'll explain you the same thing that you know already in 4 different ways. So there should be a chance to pick up on one of them. And then I hope to get to this one in the end here. So here's my own slightly simplified, same as before. Here's the resonator. Just think of it as a classical LC resonator for today, linear response from this matter system here, which consists of a superconducting circuit. So I need to think of the flux being induced by currents over here, and then a source drain, superconductors, and a quantum dot in here with a single electron having a spin. And this is all written up in this paper here, and it is really the efforts of Cecilia Hermansen, my PhD student and collaborator in Copenhagen. Yu-Shiba and Rusinov all need to be thanked for this phenomenon here, although they all talked about classical magnetic moments, and that wouldn't work if this was a talk about Kondo effect, because then it has to be a quantum spin that can flip. That's crucial for the Kondo effect, but it's not crucial for this effect. For this effect, it's just a question of superconductors not liking spin polarization because of the singlet pairing. So that's a slight difference. So Rusinov, for instance, let's take his version of it. He just considered a spin-dependent potential, a local potential in a superconductor. It has potential scattering, or it has something that depends on spin now. But it's just a local magnetic potential in a superconductor. But you see, it's just a tau set here. It's just a set Pauli matrix, so really no spin flips involved in this. And then you get some bound states at this impurity inside the superconducting gap. You can parameterize them with phase shifts if you like. But the potential scattering and the, here I call it JS because I'm going to think of a spin. I'm going to think of a magnetic moment of this, and I'm going to think of an exchange coupling later on. But really it's just the strength of the magnetic component. So these subgap states depend on this JS. If J is not there, you don't get anything. Then it just moves back up to the gap here. But as you increase the magnetic component or the spin-dependent component of this, you get a subgap state that moves down and crosses zero energy. And then the ground state really changes of the system. Right? And eigenfunctions in 3D, they would look something like this. So they are localized on the scale of the coherence length exponentially, but they also have this 1 over r, or, depending on the dimension here. It's really just sort of the superconducting Friedel oscillations around this magnetic impurity. And as I said, normally you would see this in STM, like manganese or chromium on lead here, would look something like this. So you can see it in the spectroscopy with STM. And they have a lot of personality, teaches you a lot about these add atoms. But today I'll just think of a very simple impurity, namely a quantum dot. So think of a single orbital described in an Anderson kind of model. So local interactions could be strong. And then I just hybridize with a normal metal, except that the normal metal has now gone superconducting and opened a gap. First things first, let's say if the gap is very, very large compared to the interactions, then you don't care much about the interaction because you really don't want to have single electrons out in the superconductor. So if you want to make all the electrons reside. You sort of proximitize the level here. And if you solve this problem here in the infinite gap limit, you can integrate out the superconductor if you like, and then you really just get proximitized levels out of it, right? With the interaction still, but the ground state will be a combination of 0 or 2 electrons on the dot or on the level here. And then there's an excited state with either 0 and 2 again, and in between there's a doublet. And they have these energies here, and you can work out everything. It looks something like this. So Xi d is now this level here plus half of the interaction strength. So when it is 0, I'm at particle hole symmetry. So it's taking out an electron or adding an electron to this level is the same. So that's at this point here where there's exactly 1 electron on the dot if it was normal. But in this case, it is superconducting with a very big gap. So you just proximitize it, and this becomes the ground state here. Well, not in here. You see in here, the doublet actually wins for the parameters it shows here. So here, the red state is the ground state. And this blue state will be that one. So I have to move out a little, and then it becomes favorable for this proximitized ground state to win. And the others are up here. So this excitation spectrum here is just of these 4 states here. Here's the spin doublet, and then 2 singlets here. And if I go to this line here and look at the phase dependence, because I have two superconductors added in here, I really added an extra superconductor. So I can talk about the phase difference between those two superconductors. Then these energy levels would disperse something like this here. So that's the infinite gap limit, very simple limit. You can do everything. You can plot the ground state phase diagram like this. If you are close to here, then the doublet is the ground state, unless you increase gamma, which is the hybridization strength. It is T squared times the density of states of the lead here. Right? So if the hybridization with the lead increases, then you switch from the doublet state to the BCS ground state. And you won't have this doublet phase in here anymore. By tuning the gate out here or tuning the level out here, you can also leave the doublet phase. Now, if you take the gap away from infinity and down to a finite number, nothing much happens really. This moves down, this dome here, this phase boundary here to the blue here, where it's even very small. And so, okay, it's practically the same, except the states here become hard to write down. So in the limit where delta is 0, you get a Kondo screening singlet. I wouldn't know how to write it down, but I would know who to call to have a numerical version of that ground state. But it is a singlet. It's a complicated phenomenon of screening the doublet, screening the spin, right? That happens when there's no superconducting gap here. But here it's easier. There is a doublet ground state until the superconductor prefers to proximitize the level instead. So in this limit where U is larger than delta, it is more like a Kondo phenomenon. This is where this Yu-Shiba-Rusinov logic works again. So I just want you to keep this in mind. It is not entirely, I'm missing the gamma here, but think of something like this. If the gap is very large, just think of proximity effect. If U is very large, the gap hardly matters. It would just be Kondo effect, where this magnetic moment is screened by an extra quasi-particle. If you're in between, then you might not like to put the quasi-particle entirely in the BCS gap because you have to pay the gap. So you place it here or there or somewhere in between. So you interpolate between these two. So that's the picture of this fruit fly I would like you to have in mind. Okay, just to connect with Rusinov's calculation here, let me go from the Anderson model and say if U is very large, then let's think of tuning the gate so that the level such that there's always one electron on the level nominally, except for the superconducting influence. Then I could write down a model that looks like a Kondo model here, exchange co-tunneling model. Now I'm thinking of a quantum dot here and two superconductors. So I co-tunnel, I jump here virtually and back and forth, and likewise over here, I go here and over there. So now there's two channels and some indices alpha here taking care of that. But basically there's a potential scattering term and there's a magnetic scattering term like in Rusinov's formula here. And therefore you can do roughly the same thing. I make these couplings dimensionless, G and little w. I have to take care of the asymmetry of the couplings here, so there's some left-right indices here, don't worry about that. And the phase difference lives in these terms when I go from one to the other. And these depend on x, which is my level position. So it's this level position here. So x is 0 when I'm at particle hole symmetry with this level here. And this is just shorthand for something that appears in this formula that you shouldn't stare at very long. It's just to say that now it's simple enough that you can do it analytically. And there's some formula and it looks like this. You can take a few limits just to check, if there's no phase difference, like Rusinov didn't have, he had one superconductor, then you get back to his result. And this phase shift is exactly like he had, so exactly the same physics. If now I say that the spin is polarized, you see up here, I kept the S dot sigma, so I'm ready to do Kondo physics. I have spin flip terms and all. So I drop those now. I say, let's say this is only along a set, and that's where this works. Otherwise, I can't solve it exactly. Right? So it is exactly mimicking Rusinov's solution. Another well-known result is the one I first showed you on the first slide, this Benacker result for a short SNS junction. So if I remove the magnetic feature here, it's just a potential scattering model. It's a co-tunnel junction with no magnetic properties, no spin dependence, and you recover this result with this transmission here, just depending on the potential scattering. So this is a nice and simple model. You can do things analytically and enjoy yourself with that. And you can calculate the supercurrent. You can see how the junction depends on phase. You know, the current here depends on phase as a sign here, more or less, for large exchange coupling, large magnetic component here. Then it becomes just a zero junction, as we would say, normally Josephson junction. But if the coupling is not so strong, then it is actually a pi junction. So it goes the other way. You know, it goes down before it goes up. If it's somewhere in between and the asymmetry is like here. So pi fourth for this theta here is symmetric coupling. I'll be using that a few times. But it's just to say if it's in between here, then you have situations where it thinks it's a zero junction and it decides, no, better stay on the pi branch. So you have these discontinuous things. If you stay in the ground state with this system, then the supercurrent will have these discontinuities. So these are zero prime and pi prime, if you like. Okay, and to summarize what we know about this fruit fly, with already in 92, Sartori here had a paper where they worked this out with numerical renormalization group, and they all agreed here that you change from a doublet to a singlet, increasing the magnetic component of the scattering. This happens universally when the condo temperature is at 0.3 delta. Same by Johannes Bauer and company up here. They plot the phase diagram like this, and NRG calculations also match. So actually NRG is the crosses and triangles here. So everybody agrees on this phenomenon. So it's a nice, non-trivial, but still simple hybrid system to fool around with if you want to understand how simple things work. Here's the quantum dot version of it. If you like Coulomb diamonds, which I have been liking for some 10 years now, 20 years, sorry. Oh, time flies. But they have been a friend for many of us for many years. You see this and you know that the device is Coulomb-blockaded. You know that charge is a good quantum number. Here is a gate voltage, and you just fill in electrons one by one. So 1, 2, 3, 4, 5, and so on. This is in 150 millitesla to make the let's see, what's the superconductor here? It's titanium aluminum. So that's this shiny thing here, and this is titanium gold. So to make this normal, you apply 150 millitesla in plane, and it looks very normal like this. This is a normal, dI/dV curve as a function of gate voltage here. If you remove the superconducting, if you remove the suppression, then it becomes superconducting. You see the gap in here, and then you see all these subgap states that I just told you about. This is, this is a doublet ground state. This is one spin on the dot. This is no spin on the dot. This is one spin on the dot, and so on. So spinful, spinless, spinful, spinless, 1, 2, 3, 4, 5, and so on. And over here something else happens, and that's because now the exchange coupling was strong enough to make the singlet the ground state. And I had this option as well. So this is a nice clear view of what happens here, and you can gate it through a lot of different of these, and you can go and study these. And again, this is a junction like this, 330 nanometers apart. It looks like some of the devices we have in the previous slides, except that here it was not the epitaxially grown material. So this is old generation stuff. So back to this, we need to do one more calculation, and then we are off the hook, I think. To describe the LC, there's a resonance at this frequency here. It has this impedance. There's the quantum of resistance, and this mutual inductance here. I made dimensionless here, putting the 0-point fluctuations of the phase here, and then this M over L here. And this is then what I just described you, and the question is, what is the admittance of this? If I know that, then I'm done. So we do it in linear response, Kubo formula. The Hamiltonian here that I had from before is shifted by this much when I couple the two here. And so Kubo formula tells me I need to calculate the current correlation function, so that's where the hard work is for this model here. And then, there's also some change to the current operator itself that goes this way here. And you can Fourier transform, that works. You can then say, if you do this at zero frequency, you can get the adiabatic change in the current like this derivative here. So that's dividing this by this at zero frequency. So therefore this derivative must be equal to this at zero frequency. So that's this formula here. So now I can express this term here in terms of the other two. So I can rewrite this as this derivative. So now I just have to calculate the supercurrent and take the phase derivative, or the second derivative of the ground state energy as a function of phase, if you like. And then the delta chi here is just the difference between the dynamic and the static current correlation function. With this object here, I get the frequency shift and the damping, and then we're done. So that's all I'm gonna say something about. And I'm gonna try to say as little as possible, because you do the calculation and either you can do it or you cannot do it. And it works in these cases I show here very nicely. Just to warm up the infinite gap limit with these states here, let's do that again. We know them from before. I have a tunnel coupling to left and right superconductor. I parameterize them again with this theta angle. Here's the gamma. And I have some little gamma now that enters these energies here, and they depend on the phase. So now these energies depend on the phase, so then the supercurrent comes out as the derivative of these energies, and the inverse inductance comes out as the phase derivative of those. And we need to get to this. And if you do this calculation, it's very simple. You can express it like this here. Here's this EA, it is here. And you find this result here. And there's a matrix element here, which also is very simple to write down. So choosing some parameters here, close to but not quite symmetric coupling at the particle hole symmetric point, and some arbitrarily chosen resonator frequency of 0.45 of gamma. Then if I'm in the minus state here, the lowest lying of the even parity state, I'm going to say parity now because there's an even number of electrons in this state. This would be odd parity, there's an odd number, so even and odd parity states. If I'm in that state, then the frequency shift would look something like this here. Here I put the resonator frequency here, and this is the energy of the excitation between these two states here. And here I'm showing you really the real part of this response function here, which is the frequency shift. So it's quite moderate, and then it has this singularity here when it's in resonance with the transition in the system. And so it looks like that. If you had been in the plus state instead, which is an excited state, but who knows, maybe you're not in a ground state, then the response would look like this. I compare now with this paper here, which is the same as this, but with a perturbatively included effect of the interaction. So weak interaction corrections to this also give, the dark blue looks like my dark blue. I chose the same parameters. The light blue is a little different, and the orange here is because the doublet also has some phase dispersion now and gives some inductive response. Okay, so there's a slight difference when you include that, and the gap is no longer infinite. Okay, but close enough and very easy calculation to warm up with. Now let's go to the one where I did the Schrieffer-Wolff transformation. I had my Kondo model. I said no spin flip, and it's basically Rusinov for quantum dots with two leads. I had this closed form expression here. I show you the single particle spectra here. So this is for weak exchange coupling, so my gamma over U is not so large. The coupling to the leads squared, so this is the virtual tunneling in and out of the dot. So I have a doublet ground state, except it's not really a doublet because I polarized the spin. So had it been quantum spin, it would have been a doublet. Here it's an unscreened magnetic moment. Whereas these are the ones where there's no magnetic moment. You see, they have a quasi-particle in here with spin down. So they are trying to screen this moment, which is spin up. And they try it in each their own way. The blue one here is the one Rusinov found when he had only one lead. I have the option of having a symmetric or anti-symmetric mix of the two leads now. So it's a two-channel problem, so I have two screening channels. So I can put the spin down in this one or in that one. But the odd component, the odd, the left minus right screening channel is really not a subgap state until you start using the phase, because the phase knows about left and right, and then it moves into the gap. If I increase the gamma here, I change the, I stabilize now a region of screened state here. So this thing crosses down through zero energy. So the ground state here is a screened magnetic impurity. There's a quantum dot, a polarized spin, and then there's a quasi-particle screening that magnetic moment. If it's not a superconductor, it would have been the condo singlet. But this is simpler because of the gap. And then over here, this phase, you can't sustain the screening anymore, and you give up, and then you're back to the doublet or the unscreened state. And then you see now the odd channel has moved deep into the gap. And it's interesting to note this gap here because they are between states of the same parity. They both have a screening quasi-particle roaming around. So with photons, with microwave photons, I can only go between particles with the same parity because it's modulo 2 electrons. I can't make excitation in the system that change the electron number. So no, I have to maintain the parity.
And you see this avoided crossing because you have asymmetry in the coupling?
Yes, this is an asymmetry. You can close this gap if you have symmetric coupling and particle-hole symmetry. As if everything is, am I forgetting something? At least left and right symmetry and particle-hole symmetry. Yeah, then you close this gap.
Pi and 0 you will have closing.
Yeah, yeah. Okay, and this is also a little confusing to look at. So here I did you the favor of working out, okay, here's the ground state. It's an unscreened ground state all the way through here. And here's its energy and how it depends on phase, because now you can take the derivative and find the supercurrent. Here are the excited states. They are screened, and this is the excitation energy, right? But this is odd parity, and these are even parities. You're not going to have a microwave transition between this and these two. You might have one between this and that, but that requires that you are not in the ground state. Right, so you can always infer these, or already now you can infer these things. Down here, it's a little different. Now at phase difference close to pi, I can stabilize the singlet ground state, and then I can excite with microwaves up to the other singlet because they have the same parity. If there is a matrix, we still need to calculate that. But that's how the many body states, the eigenenergies of this system look. And this is a little confusing. This is the single particle excitation spectrum. But anyway, it's just, combining things from here, you get this. And I will use this unscreened and screened synonymously with if you had an unpolarized spin, which I really do. I'm just simplifying things because then I can stick to this calculation here. I'll liberate that in a moment. So then this would have been a doublet ground state, and this would have been a singlet ground state. So unscreened is the untouched magnetic moment. And here I just want to do a proof by intimidation that I can write down in closed form what the matrix element is. And that's wonderful, and there's no typos, I'm sure. Right? And okay, you stare at this and you don't care much, but you want to take the limit where there's no G, because then you can compare to this paper here by Koss and Glassman, where they did a weak link and did the same calculation. And then you get exactly the same formula, which is, it still has some terms in it. It's simpler than this, but it's nice, you connect with it. But if you plot this thing instead as a function of, so now phase difference, X is deviation from particle-hole symmetry, so the level is moved to the side. So here is when you are in the middle, you have one electron on the dot if it hadn't been for the superconductor. And if you change the asymmetry, you move it a little to the side here, then you go along this axis. And here I show you the matrix element, but I show it to you only when I'm not in this region where the doublet is the ground state. This is regrettable because, you know, usually these systems, they don't care much for being in the ground state. Some systems do, some systems don't. So, you know, I should have maybe plotted the whole thing here, but I want to indicate here that this is how well you absorb microwaves, except if you're in the doublet ground state, you don't absorb anything. So that's what this means, right? And if you go over here, it is the left-right coupling to the two superconductors. Here it's symmetrically coupled. Here I decouple one completely, and then of course there's no matrix element because there's no current fluctuation. Right? It is no longer an Anderson model. I did a Schrieffer-Wolff transformation, so I integrated out all charge fluctuations, so I just have a magnetic moment here and nothing happens. In this co-tunneling model, you can just see that it's there, but it's only when you have two leads you can go across and really carry a current. And then you see a matrix element here. So this is because I'm a little brutal, I'm doing this large U limit, I don't capture the right physics out here that would be in an Anderson model. So anyway, you see that this formula gives you something, and okay, now you can stick this into a computer and plot what you like. So that's what Cecilia is doing here. She took the imaginary parts. They're easiest to calculate, but really you just do it numerically with, you know, plug in this analytical formula and evaluate it. And then you sum up these three terms. Here's the inductive response, just the phase dependence of the supercurrent. Here is the other part, and part of it we call resonant because it lives below the gap. And it is something you can write out exactly like the matrix element I showed you times this delta function. So it's something you really know analytically how it looks. And the other thing is less interesting. It lives up here in the continuum because it's exciting one quasi-particle directly up into the continuum and taking one from the subgap state as well. So this is how the imaginary part looks, and then you can do some, you know, complex analysis and find the real part. So it looks like this here. And now I know the frequency shift. So now I'm ready to calculate those because I know all this stuff. And here I chose some parameters. Symmetric coupling to left and right. Some resonator frequency in units of the gap. It's slightly above the gap now. And then a little bit away from particle-hole symmetry here. Over here it's particle-hole symmetry, X is 0, but then the left-right coupling symmetry is broken. Here is the two-particle excitation spectrum. So there's now a chance that the resonator frequency will cross this excitation energy, and I could see this thing down here that we saw on the very first slide. Here's the inductive part, just the phase derivative of the supercurrent. Here's the resonant part. It has this thing, and here I show you what happens if I'm in the continuum here. That's the orange line, is this less interesting curve. You know, it has some features, but it's mainly the resonant feature here is interesting. If you add everything up, you get something that looks like this for a system that's in its ground state, right? And in this blue region here, it is in its doublet, well, not, but in its unscreened ground state, right? And that's why you see this discontinuity here in the supercurrent. Remember, it had these features here. So I removed the infinity here, you know, because taking the derivative of this is not so cool. And here I do it again for parameters where there happen to be no unscreened region in the middle here. So, okay, that's how it looks. So let's try to do another calculation where I don't have to say that the spin is polarized. Instead, I do something utterly ridiculous. I say, what if the superconductor only has one quasi-particle? So here's the density of states for the superconductor. That seems very childish, and it was a great advent in these couple of papers here. And it works like a charm, because really all I need for this physics is one quasi-particle to be there to screen the spin. I don't care about the other ones for the subgap states. The continuum will be completely wrong. I won't capture anything of that, but the subgap physics is great. You could say maybe I need 1.5 quasi-particle. That's true, and then this is not entirely exact. For Kondo effect, you might need 10 quasi-particles. Who knows, but then there's no gap. So the gap is a great friend here. It makes the problem much, much simpler. And even this ridiculous model here, which you can solve very easily, captures most of the physics. So to do that, Gorm was kind enough in his master thesis to work out for this quantum dot we had. We were looking at the single particle excitation spectra. So here is gate voltage, here's particle hole symmetry, and here's bias voltage. So we were always looking at pictures like this. And Anders Jellinggaard, he was doing experiment, but in his spare time he cooked up an energy code that made these plots. So this is the numerically exact solution. And then Gorm was wondering back then, could I fit these by the zero bandwidth model? And the answer seemed to be yes. I mean, to every picture here, there's a picture here that corresponds to it. They are not in the same coordinate. This is not the same as there, the same value of u and gamma. So you have to tweak these models here, obviously, because gamma knows about the density of states of the BCS lead. So no wonder that you have to fiddle with the numbers a little bit, but you get the same pictures. So you can fit energy with zero bandwidth when it comes to the YSR subgap states, more or less like this. So let's proceed with this. Here it's a 64-dimensional Hilbert space. You just, do, here's the formula for the current correlation function. You know all the eigenstates and so on. So there's no questions left. You just have to live with the fact you don't know anything about the continuum anymore. But for the resonant component, you know everything. And here's plots, same but different. They look a little bit like the ones before. I hope you agree with me. And it's from this simple model here. So if I compare the two, then the dashed line here is the polarized spin approximation, and the full lines are zero bandwidth. Here are these annoying single particle excitation spectra, and you see dashed. Oh, it's not doing very well, this zero bandwidth. They don't match very well. But I chose parameters where they both had a chance to work. I need u much larger than gamma, and that's satisfiable here. So it's a fair comparison. But if you go to the two-particle excitation spectrum, it looks much, much better. And that's the only thing that's relevant for the microwave absorption. And indeed, if you compare, you have the inductive and the resonant component, and you compare the total here. The dashed is Rusinov's version here, and with two leads, and the full line is the zero bandwidth. You roughly agree on what's going to happen, right? So they compare fairly well. So now the only question left is how lousy is the zero bandwidth really? And then came along Virgil here. He was doing nuclear physics and knew all sorts of nice methods for many particle systems, including a very nice DMRG code. So he was kind enough to repeat this with not one level, not one state, but 20 states. And the Hilbert state space is now large, but with DMRG he can just keep the lowest states and repeat the calculation. So I said, here are my favorite parameters for the zero bandwidth. That's the blue line here. Single particle, two particle spectrum here, and the response, the microwave response here. Try to use the same parameters and use 20 levels. And then Virgil says, well, then I get the red ones. So it's not quite the same. But if he then readjusts the tunnel coupling slightly, because we don't know the density of states still, and this is, I could place these levels in many ways, then you can fit it, with this number, you get back exactly to the zero bandwidth. Well, exactly, except for this feature here. That's the only difference we really see. You see the response over here is practically the same. Orange is the same as the blue. Here there's a slight difference because now Virgil is describing the continuum better. I mean, there's more states to push my subgap states a little further down into the gap. And that's the detail you have to live with if you use zero bandwidth.
Sorry,
And if you
Yeah.
compare,
the blue is zero bandwidth.
The blue is zero bandwidth, yes, and the orange is the DMRG fit with 20 levels to the zero bandwidth.
if you compare with full energy, including all the
That's the same as the DMRG.
But only
But-
with 20 levels you would
Yeah,
compare 20
I'm-
levels
I'm-
with the full calculation? You
I'm
already
pretty sure. That's what Rock and I forget some, but Pavicic were doing this paper here.
I see.
So Virtual was just copied what they did here, really. So I don't recall if they benchmarked it. To what extent is this enough to get Kondo? I'm not really sure, but I would think it's plenty. Well, let me not think anything. Let's look up in the paper here. But for this, this is exact now. Okay, and then back to this experiment here. So here I put their numbers, and here are their fits, and we appreciate perhaps that these curves look a little bit what I showed you now. You might wonder, why is there a superposition of both? But that's most likely because the system is not in its ground state, because there's quasi-particles entering and leaving the system. So now you think you're in an even parity state, and then comes a random quasi-particle and poisons the system, and then you're in an odd parity state. So it's really not allowed to quasi-particle relax to the ground state, apparently. So you superimpose the unscreened and the screened state. They had different responses. And with the zero bandwidth, I tried to fit this as well. And I would use these parameters here. So one would hope that the aluminum gap was close to its nominal value of 45 gigahertz. Here they are at 25 and 28. Here I can manage with 37, so I'm a little more happy about that. But first and foremost, what I prefer in this fit is that I can keep the same value of the interaction strength here at 1 and 1.5. So to me that's rather convincing, but these are taken at different gate regions in the same device. So the first thing you will think is that maybe not the charging energy and maybe not the gap would change, but maybe some asymmetries and so on. And that's indeed all we have to change here. The tunnel coupling is slightly different in the two, and the asymmetry is slightly different. But the other parameters stay the same, and we chose particle-hole symmetry like they did here. So it's just to say that I would tentatively say that perhaps this experiment is really a case of microwave absorption in a Yu-Shiba-Rusinov state, and not in a weakly corrected resonant level. A resonant level is the non-interacting version of the Anderson model with a little bit of interaction. So that's the conclusion for this. If I do Virgil's fit of it, again, it's the same story, the orange. So whether I fit this by zero bandwidth or I ask Virgil, it's just going to change the value of this t, and nobody has any opinion about what t is because you can't measure it anyway. So that's that conclusion. So what we learn from this is hopefully that interactions in this system, not in the SNS system I showed you in the beginning, where Francisco and Alfredo, they did a fit with more states involved and more personality to the subgap states. There, a mean field interaction seemed to work fine. Here it's sort of the opposite limit. You have one level, you have an Anderson model and Kondo and whatnot, and then that seems to work fine as well. You can tune it with phase or with gate, I should add, because only this year again came this beautiful paper from the group at Delft, where Ramon was working out the theory again with Rock Sitko as well, and Arno and Marta were doing this experiment, as far as I know, with Bernard. And you see a resonator, you see a circuit here. Here's the quantum dot, and now there's a transmon over here. So that just increases visibility somehow. So let's not go into that. I just want to show you this nice transition here as a function of gate. VP is a combination of two of these gates here, as far as I recall. So you can tune this quantum dot and go through. So the frequency shift seems to follow the transition from singlet to doublet, and that's beautifully explored in this nice experiment here. So if the phase here is fixed at 0, it looks like this. That's this. If you fix it at pi, it switches around and looks like this. So it's a very nice example as well, and a beautiful experiment. So that was the phase or gate. And only the screened singlet, the screened magnetic moment, absorbs microwaves. Right? So that's the other message here. It's a 2-channel problem, otherwise there's no current. So you need at least 2 channels. You could have 3 channels. Multi-terminal would also work. It's something we are working on now, and it generalizes very nicely. And the dispersive shift is, quote unquote, well captured by zero bandwidth approximations. There are a few corners of parameter space where I have a warning sign, but then you should go to the DMRG and include a few more levels, and then all is well. But the nice thing about the other simple models is that you can understand things even analytically in some cases. So you get a good feeling for the physics going on here. And basically, I just want to summarize it as the transition from the resonant level with perturbative interaction corrections up here, proximity effect plus a little bit of U, and then down here in the other limit where we do YSR. And then, of course, there's the mess in between, which is the hardest region. But you know both corners here, so I think with these methods here, you can easily interpolate between the two. So with that, I think I should actually stop here. I think this clock is unfortunately accurate, I think. So with that, let me thank you for your attention.